For centuries, the universe was viewed as a giant clockwork, predictable and precise. This was the era of classical physics, ruled by Isaac Newton's laws of motion. These laws described a deterministic universe if you knew the initial conditions of a system, the position and the momentum of its parts. You could, in theory, predict its future with absolute certainty. This deterministic view permeated scientific thought. It was a time of great confidence in the power of reason and observation. Scientists believed that the universe held no secrets, that everything could be measured and understood. The universe was a giant equation waiting to be solved. This confidence was epitomized by the concept of Laplace's demon. This hypothetical being, possessing infinite knowledge and computational power, could know the state of every particle in the universe. Armed with this knowledge, Laplace's demon could predict the entire future with perfect accuracy. It was a powerful, if unsettling, image of a universe devoid of chance or surprise. While Laplace's demon was a thought experiment, it reflected the prevailing belief in the power of deterministic laws. The universe, in this view, was an open book. All that was needed were the right tools and intellect to decipher its secrets. This belief fueled scientific progress for centuries, leading to countless discoveries and advancements. However, as scientists delved deeper into the nature of reality, they began to encounter phenomena that defied classical explanations. The neat, predictable world of Newtonian mechanics started to unravel at the edges, revealing glimpses of a stranger, more elusive reality beneath. One of the first cracks appeared with the study of light. Classical physics treated light as a wave, but experiments like the photoelectric effect showed that light also behaved like a particle. This duality of light wave and particle challenged the classical framework, hinting at a deeper, more complex reality. Another anomaly emerged from the study of heat radiation, specifically the problem of black body radiation. Classical physics failed to explain the observed spectrum of light emitted by heated objects. The solution, proposed by Max Planck, introduced the concept of quantized energy, suggesting that energy could only exist in discrete packets or quanta. This radical idea challenged the classical notion of energy as continuous and laid the groundwork for the quantum revolution. These early discrepancies, though seemingly minor, were like hairline cracks in a seemingly solid foundation. They hinted at a fundamental flaw in the classical worldview. The universe was not behaving as expected, and scientists were forced to confront the possibility that their understanding was incomplete. A new theory was needed, one that could accommodate these strange new phenomena and provide a more accurate description of reality at its most fundamental level. This need gave rise to quantum mechanics, a revolutionary theory that would shatter the deterministic worldview and usher in a new era of scientific understanding. At the turn of the 20th century, the world of physics was on the brink of a revolution. The anomalies observed in light and heat radiation were just the tip of the iceberg. As scientists probed deeper into the atom, they encountered a realm where the familiar laws of classical physics seemed to break down. The microscopic world was proving to be a bizarre and unpredictable place, governed by a completely different set of rules. One of the most perplexing phenomena was the behavior of electrons in atoms. Classical physics predicted that electrons, being charged particles, would continuously emit radiation as they orbited the nucleus, eventually spiraling into the center and causing the atom to collapse. However, atoms were remarkably stable, defying this classical prediction. Clearly, something was amiss. In 1913, Niels Bohr, a Danish physicist, proposed a radical model of the atom that incorporated elements of quantum theory. Bohr's model postulated that electrons could only occupy specific, discrete energy levels within the atom. Electrons could jump between these energy levels by absorbing or emitting quanta of energy, corresponding to specific wavelengths of light. This explained the discrete spectral lines observed in the light emitted by atoms. Bohr's model, though a significant leap forward, was still incomplete and raised more questions than it answered. It provided a set of rules for the behavior of electrons, but offered no physical explanation for why these rules existed. The underlying nature of the quantum world remained a mystery, a realm where intuition failed and classical concepts no longer applied. The search for a more comprehensive theory of the quantum world led to the development of quantum mechanics in the 1920s. This new theory, spearheaded by physicists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, marked a radical departure from classical physics. It abandoned the deterministic worldview, embracing instead a probabilistic description of reality. Quantum mechanics introduced the concept of wave-particle duality, suggesting that particles like electrons could also exhibit wave-like properties. This duality was not a contradiction, but rather two sides of the same coin, a fundamental aspect of the quantum world. The wave-like nature of particles was described by a mathematical function known as the wave function, which contained all the information about the particle's state. However, unlike classical waves, which described physical quantities like water height or air pressure, the wave function in quantum mechanics did not have a direct physical interpretation. Instead, it was Max Born who proposed that the square of the wave function represented the probability of finding the particle at a particular location. This probabilistic interpretation was a radical departure from classical physics, where the position and momentum of a particle were considered well-defined quantities. The probabilistic nature of quantum mechanics implied that the outcome of a measurement was not predetermined, but rather governed by chance. This inherent uncertainty was not due to limitations in our measurement techniques, but rather a fundamental aspect of the quantum world. The probabilistic interpretation of quantum mechanics, coupled with the wave-particle duality, led to a revolution in our understanding of reality. It challenged the classical notion of an objective, observer-independent world. This new worldview was crystallized in the Copenhagen interpretation, largely shaped by Niels Bohr and Werner Heisenberg. The Copenhagen interpretation posits that quantum systems do not possess definite properties prior to measurement. Instead, the act of measurement forces the system into a definite state. This is not to say that the observer creates reality, but rather that the observer and the observed are inextricably linked in the quantum world. This interpretation implies that the properties of a quantum system are not inherent, but rather emerge from the interaction between the system and the measuring apparatus. This inherent uncertainty in the quantum world is not a reflection of our ignorance, but a fundamental limit on what we can know about a system. The Copenhagen interpretation, while widely accepted, was not without its critics. Albert Einstein, in particular, was deeply troubled by its implications. He famously remarked, "God does not play dice with the universe," expressing his discomfort with the probabilistic nature of quantum mechanics and the apparent abandonment of objective reality. However, despite the controversies and philosophical debates it sparked, the Copenhagen interpretation remains a cornerstone of our understanding of the quantum world, laying the foundation for further explorations into the mysteries of the subatomic realm. Werner Heisenberg, born in 1901, emerged as a leading figure in the burgeoning field of quantum mechanics. His journey into the heart of the atom began with a fascination for mathematics and a desire to understand the universe at its most fundamental level. Heisenberg's intellectual curiosity led him to the University of Munich, where he studied under renowned physicist Arnold Sommerfeld, a mentor who fostered his exceptional talents. Sommerfeld recognized Heisenberg's brilliance and introduced him to the forefront of theoretical physics, where the old classical framework was crumbling under the weight of unexplained phenomena. The young Heisenberg, eager to make his mark, was drawn to the intellectual ferment surrounding the quantum revolution. He immersed himself in the works of Bohr, Planck, and Einstein, grappling with the profound implications of their discoveries. In 1924, Heisenberg received a fellowship to work with Niels Bohr at the Institute for Theoretical Physics in Copenhagen, a hub for the world's most brilliant minds wrestling with the enigmas of the quantum world. It was a pivotal moment in his career, placing him at the epicenter of the quantum revolution, where he would collaborate with giants like Bohr, Pauli, and Born. The atmosphere at Copenhagen was electric, fueled by intense debates, radical ideas, and a shared passion to unravel the mysteries of the atom. Heisenberg thrived in this intellectually charged environment, engaging in lively discussions with his peers, challenging established notions and relentlessly pursuing a deeper understanding of the quantum realm. His time in Copenhagen would prove to be a turning point, not just for his own scientific journey, but for the future of physics itself. Heisenberg's work on matrix mechanics, a revolutionary mathematical framework for describing quantum phenomena, exemplified his unique approach to scientific inquiry. While classical physics relied on visualizable concepts like particle trajectories and continuous motion, Heisenberg's matrix mechanics abandoned these intuitive notions, embracing instead a more abstract and powerful mathematical language. Matrix mechanics emerged from Heisenberg's conviction that physical theories should be based solely on observable quantities. He argued that since the electron's orbit within the atom could not be directly observed, it was meaningless to assign it a definite trajectory. Instead, he focused on what could be measured, the frequencies and intensities of light emitted by atoms when electrons transitioned between energy levels. Heisenberg's breakthrough came when he represented the electron's energy levels and transition probabilities as matrices, mathematical arrays of numbers that could be manipulated according to specific rules. These matrices, unlike ordinary numbers, did not commute, meaning that the order of multiplication mattered. This non-commutativity, a radical departure from classical mathematics, turned out to be a key feature of the quantum world. Matrix mechanics, though mathematically rigorous and successful in explaining experimental results, was initially met with skepticism and resistance. Its abstract nature and lack of visualizability made it difficult for many physicists, accustomed to the intuitive pictures of classical physics, to grasp its significance. Even Heisenberg's mentor, Niels Bohr, initially expressed reservations, finding the formalism too abstract. Section 3. The Seeds of Uncertainty. Challenging classical assumptions. Despite its initial abstractness, matrix mechanics, along with Erwin Schrödinger's wave mechanics, formed the foundation of modern quantum theory. These two seemingly different approaches, one based on matrices and the other on wave functions, were eventually shown to be mathematically equivalent, each offering a different perspective on the same underlying reality. At the heart of both matrix mechanics and wave mechanics lay a profound departure from classical physics. The realization that certain pairs of physical quantities like position and momentum could not be simultaneously known with arbitrary precision. This inherent uncertainty was not a limitation of experimental techniques, but a fundamental principle woven into the fabric of the quantum world. This principle, which would later be formalized as Heisenberg's uncertainty principle, emerged from the non-commutativity of matrices in his theory. Heisenberg realized that the act of measuring one quantity, say the position of an electron, inevitably disturbed its momentum and vice versa. The more precisely one quantity was measured, the less precisely the other could be known. This inherent uncertainty was not due to any deficiency in the measuring apparatus, but rather a fundamental property of quantum systems. It challenged the classical notion that particles possess well-defined properties independent of observation. The very act of observation in the quantum world played a crucial role in defining the state of a system. This profound insight would have far-reaching consequences for our understanding of reality itself. In 1927, Werner Heisenberg unveiled one of the most profound and revolutionary concepts in the history of science, the uncertainty principle. This principle, born from the depths of quantum mechanics, shattered the deterministic worldview of classical physics, revealing a fundamental limit to what we can know about the universe at its most fundamental level. Heisenberg's uncertainty principle, stated simply, asserts that certain pairs of physical properties, like the position and momentum of a particle, cannot be simultaneously known with arbitrary precision. The more precisely one property is measured, the less precisely the other can be determined. This inherent uncertainty is not a reflection of limitations in our measuring instruments or experimental techniques, but a fundamental feature woven into the fabric of the quantum world. Imagine trying to pinpoint the exact location and speed of a tiny, fast-moving particle like an electron. In the macroscopic world, this task seems straightforward. We can track the trajectory of a baseball or a planet with remarkable accuracy. However, in the quantum realm, the act of measurement itself introduces an unavoidable disturbance to the system being observed. When we attempt to measure the position of an electron, for instance, we need to interact with it using some form of probe, such as a photon of light. This interaction, however unavoidable, imparts momentum to the electron, altering its velocity in an unpredictable way. The more precisely we try to determine its position, the more we disturb its momentum, and vice versa. And the uncertainty principle arises from the wave-particle duality of matter, a core concept in quantum mechanics. Particles, like electrons, can exhibit both wave-like and particle-like behavior. This duality is not a contradiction, but rather two sides of the same coin, a fundamental aspect of the quantum world. Waves, by their very nature, are spread out in space. They don't have a single, well-defined position, but rather exist as a distribution of probabilities over a range of positions. This inherent fuzziness is captured by the wave function, a mathematical function that describes the state of a quantum system. The uncertainty principle tells us that this wave-like nature of particles imposes a fundamental limit on how precisely we can simultaneously know both their position and momentum. It's like trying to squeeze a balloon. The more you try to confine it in one direction, the more it bulges out in another. This inherent uncertainty is not a reflection of our ignorance or limitations in our experimental techniques. It's a fundamental property of the quantum world, a consequence of the wave-particle duality and the probabilistic nature of quantum mechanics. Heisenberg's uncertainty principle had profound philosophical implications, challenging the very foundations of our understanding of reality. Classical physics, with its deterministic worldview, had painted a picture of a universe where everything had a definite place and momentum, where the future was, in principle, completely predictable if one knew the initial conditions with absolute certainty. The uncertainty principle shattered this deterministic illusion, revealing a universe inherently governed by chance and probability. It was no longer possible to speak of particles having definite properties independent of observation. The act of measurement in the quantum world played a crucial role in defining the state of a system. This realization had profound consequences for our understanding of causality and determinism. If the present state of a system could not be known with absolute certainty, then predicting its future behavior with perfect accuracy became impossible. The universe, as revealed by quantum mechanics, was not a giant clockwork mechanism, but rather a realm of possibilities where chance and probability played a fundamental role. This shift from a deterministic to a probabilistic worldview was a radical departure from centuries of scientific thought. It challenged the very notion of an objective, observer-independent reality. The observer in the quantum world was no longer a passive spectator, but an active participant whose active observation influenced the state of the system being observed. Heisenberg's uncertainty principle, despite its unsettling implications for our understanding of reality, did not undermine the power or effectiveness of science. Instead, it redefined the scope of scientific inquiry, shifting the focus from attempting to measure everything with absolute precision to understanding the inherent limits imposed by quantum laws. The uncertainty principle became a cornerstone of quantum mechanics, a key component in the development of countless technologies that shape our modern world. From lasers and transistors to medical imaging and nuclear energy, our understanding and harnessing of the quantum world with all its inherent uncertainties have revolutionized our lives. Moreover, the uncertainty principle sparked heated debates and philosophical discussions about the nature of reality, the role of the observer, and the limits of human knowledge. It forced physicists, philosophers, and theologians to confront profound questions about the nature of existence itself. Does the moon exist when nobody's looking? Does the act of observation create reality? These questions, once relegated to the realm of metaphysics, became legitimate topics of scientific and philosophical inquiry, fueled by the profound implications of quantum mechanics and the uncertainty principle. The uncertainty principle, far from being a limitation, opened up new avenues of exploration, leading to a deeper and more nuanced understanding of the universe and our place within it. It revealed a universe more bizarre, more wondrous, and far more profound than anything imagined by classical physics. Albert Einstein, a towering figure in the annals of physics, played a paradoxical role in the quantum revolution. While his work on the photoelectric effect had provided crucial evidence for the quantization of light, a cornerstone of quantum theory, he remained deeply skeptical of the probabilistic interpretation at the heart of quantum mechanics. Einstein's discomfort stemmed from his deep-seated belief in a deterministic universe, a universe governed by laws that left no room for chance or uncertainty. Einstein's famous quote, "God does not play dice with the universe," encapsulated his philosophical opposition to the probabilistic interpretation championed by Bohr, Heisenberg, and others. He firmly believed that the randomness inherent in quantum mechanics was not a fundamental aspect of reality, but rather a reflection of our incomplete understanding of the underlying laws governing the universe. Einstein's skepticism was not rooted in a rejection of experimental evidence. He acknowledged the successes of quantum mechanics in explaining a wide range of phenomena. However, he viewed these successes as provisional, suggesting that a deeper, more fundamental theory awaited discovery. A theory that would restore determinism to its rightful place at the heart of physics. This belief in an underlying deterministic reality fueled Einstein's relentless pursuit of a more complete theory, one that could accommodate the successes of quantum mechanics while also providing a causal, objective description of the universe. He spent much of his later years searching for this elusive, unified theory, a theory that could reconcile gravity, the force governing the macroscopic universe, with the strange and probabilistic world of quantum mechanics. Section 2. The Bohr-Einstein debates, a clash of titans. Einstein's skepticism of quantum mechanics set the stage for one of the most intellectually stimulating and enduring debates in the history of science. The Bohr-Einstein debates. These legendary exchanges, spanning several decades, pitted two of the greatest minds of the 20th century against each other, each challenging the other's deeply held beliefs about the nature of reality and the limits of human knowledge. Niels Bohr, the staunch defender of the Copenhagen interpretation, argued that the probabilistic nature of quantum mechanics was not a sign of incompleteness, but rather a fundamental feature of the quantum world. He maintained that the act of measurement played a crucial role in defining the state of a quantum system, introducing an inherent uncertainty that could not be circumvented. Einstein, unconvinced, countered with a series of thought experiments designed to expose what he perceived as inconsistencies and paradoxes within the Copenhagen interpretation. He sought to demonstrate that it was possible in principle to simultaneously know both the position and momentum of a particle with greater precision than allowed by Heisenberg's uncertainty principle. One of Einstein's most famous thought experiments involved a box filled with radiation. He argued that by carefully measuring the mass of the box before and after a single photon escaped, one could determine both the energy and time of emission of the photon with arbitrary precision, seemingly violating the uncertainty principle. Section 3. The Solvay Conferences, a battleground of ideas. The Bohr-Einstein debates reached their peak at the Solvay Conferences, a series of prestigious gatherings held in Brussels that brought together the world's leading physicists to discuss the most pressing issues in their field. These conferences, particularly the 1927 and 1930 gatherings, became the battleground for the clash between Einstein's classical worldview and the emerging quantum revolution. At the 1927 Solvay Conference, Einstein presented his thought experiment involving the box of radiation, confident that he had exposed a flaw in the Copenhagen interpretation. However, Bohr, after a sleepless night of contemplation, countered Einstein's argument by invoking Einstein's own theory of general relativity. Bohr demonstrated that the time dilation predicted by general relativity, when applied to the weighing of the box, precisely compensated for the apparent violation of the uncertainty principle. Despite Bohr's elegant rebuttal, Einstein remained unconvinced. He continued to devise increasingly sophisticated thought experiments, each time challenging Bohr and his colleagues to defend the Copenhagen interpretation. The 1930 Solvay conference witnessed another famous exchange, with Einstein proposing a thought experiment involving a box with a shutter that could release a single photon at a precise time. Once again, Bohr found a way to counter Einstein's argument, this time by invoking the uncertainty in the position of the box due to the very act of measuring its mass. Bohr's ability to refute Einstein's challenges, often using Einstein's own theories against him, solidified the Copenhagen interpretation's standing within the physics community. The Bohr-Einstein debates, though they never reached a definitive resolution, played a crucial role in sharpening and clarifying the interpretation of quantum mechanics. They forced physicists to confront the philosophical implications of their theories, pushing the boundaries of our understanding of the nature of reality, the role of the observer, and the limits of human knowledge. Section 1. Max Born shaping the landscape of probability. Amidst the intense debates surrounding the interpretation of quantum mechanics, Max Born, a German physicist and mathematician, made a pivotal contribution that would profoundly shape our understanding of the quantum world. While Heisenberg's matrix mechanics and Schrödinger's wave mechanics provided powerful mathematical tools to describe quantum phenomena, the physical meaning of the wave function remained a subject of intense debate. It was Born who provided a revolutionary interpretation that would solidify the probabilistic nature of quantum mechanics. Born, deeply immersed in the world of theoretical physics, recognized the limitations of classical concepts in grasping the essence of the quantum realm. He understood that the wave function, unlike classical waves that described physical quantities like water height or air pressure, did not have a direct physical interpretation. Instead, he proposed a radical idea. The square of the wave function represented the probability of finding a particle at a particular location. This probabilistic interpretation, a radical departure from the deterministic worldview of classical physics, implied that the outcome of a measurement in the quantum world was not predetermined, but rather governed by chance. It meant that even with complete knowledge of a quantum system's wave function, we could only predict the probability of finding a particle at a particular location, not its exact position. Born's interpretation initially met with skepticism from some quarters, gradually gained acceptance as it proved remarkably successful in explaining experimental results. It provided a consistent framework for understanding the inherently probabilistic nature of quantum phenomena, aligning perfectly with Heisenberg's uncertainty principle. Section 2. Embracing the uncertain, a new vision of reality. The probabilistic interpretation of the wave function, coupled with Heisenberg's uncertainty principle, painted a radically different picture of reality than the one offered by classical physics. It challenged the very notion of an objective, observer-independent world, suggesting instead that the act of observation played a crucial role in shaping the properties of quantum systems. In the classical world, objects possessed definite properties like position and momentum, regardless of whether or not they were being observed. The act of measurement merely revealed these pre-existing properties. However, in the quantum world, as interpreted by Born and Heisenberg, particles did not possess such definite properties prior to measurement. Instead, the act of measurement forced the quantum system into a definite state, a process often described as the collapse of the wave function. This collapse was not a physical disturbance of the system, but rather a change in our knowledge about the system. Prior to measurement, the particle existed in a superposition of states, a blend of possibilities described by the wave function. Upon measurement, this superposition collapsed, and the particle chose one particular state. This inherent uncertainty and the role of the observer in shaping quantum reality sparked heated debates among physicists and philosophers alike. Some, like Einstein, found this probabilistic view deeply unsettling, clinging to the belief in an underlying deterministic reality. Others, like Bohr, embraced the uncertainty, seeing it as a fundamental feature of the universe, a testament to its inherent mystery and inexhaustible wonder. Section 3. The enduring legacy of uncertainty. Despite the ongoing debates and philosophical implications, the probabilistic interpretation of quantum mechanics, championed by Bohr, became a cornerstone of modern physics. It provided a consistent and experimentally successful framework for understanding the behavior of matter at its most fundamental level. The uncertainty principle, far from being a limitation, proved to be an essential ingredient in our understanding of the universe. It explained the stability of atoms, the behavior of electrons in materials, and the interactions between light and matter. It laid the foundation for countless technological advancements, from lasers and transistors to medical imaging and nuclear energy. Moreover, the uncertainty principle forced a profound shift in our philosophical outlook on the nature of reality and the limits of human knowledge. It taught us to embrace uncertainty, not as a sign of ignorance, but as a fundamental aspect of the universe. It challenged us to rethink our assumptions about causality, determinism, and the role of the observer in shaping the world around us. The legacy of Heisenberg's uncertainty principle and Born's probabilistic interpretation extends far beyond the realm of physics. It has permeated other fields of science, influencing our understanding of chemistry, biology, and even cosmology. It has sparked countless debates in philosophy, theology, and art, prompting us to re-evaluate our place in the grand scheme of things. The journey into the heart of quantum mechanics, a journey that led to the uncertainty principle and the probabilistic interpretation of reality, has been a profound testament to the power of human curiosity and our relentless pursuit of understanding the universe around us. It has challenged our deepest intuitions, shattered long-held beliefs, and opened up new vistas of thought and exploration. As we delve deeper into the quantum realm, we continue to uncover new mysteries and paradoxes, pushing the boundaries of knowledge and refining our understanding of the fundamental nature of reality. The uncertainty principle, once a radical idea that shook the foundations of physics, now serves as a guiding light, reminding us that the universe holds endless surprises and that our quest to comprehend its secrets is far from over. The exploration of the quantum world has been a humbling experience, revealing the inherent limits of our classical intuitions and the profound interconnectedness of the observer and the observed. It has taught us to embrace uncertainty not as a defeat, but as an invitation to explore the unknown, to question our assumptions, and to marvel at the inherent strangeness and beauty of the universe we inhabit. Heisenberg's uncertainty principle, despite initial resistance and profound philosophical implications, ultimately triumphed as a cornerstone of modern physics. It wasn't merely accepted, it became indispensable for understanding the universe's inner workings at the smallest scales. The principle, once a radical challenge to classical determinism, became the bedrock upon which quantum mechanics was built and flourished. This triumph wasn't about proving one side of a debate definitively right or wrong. It was about the scientific process itself. Einstein's skepticism, though ultimately unyielding, pushed Bohr and his contemporaries to refine their arguments, to test the boundaries of their own theories, and to emerge with a more robust and nuanced understanding of quantum mechanics. The uncertainty principle, forged in the fires of these intellectual battles, emerged stronger, its implications more profound. The principle's impact wasn't confined to theoretical debates, it reverberated through practical applications, shaping the landscape of modern technology. From lasers and transistors, the backbone of modern electronics, to medical imaging techniques that peer inside the human body without invasive procedures, the uncertainty principle wasn't just an abstract concept, it was a key that unlocked a treasure trove of technological advancements. Perhaps the most significant victory of the uncertainty principle was its reshaping of the scientific worldview. It shattered the illusion of a perfectly predictable, clockwork universe, replacing it with a reality painted in probabilities and possibilities. This wasn't a retreat from scientific inquiry, but an expansion of its horizons, a recognition that the universe holds mysteries far deeper and more wondrous than classical physics ever dared to imagine. The deterministic dream of classical physics, epitomized by Laplace's demon with its all-seeing knowledge, dissolved in the face of quantum mechanics. The universe, as revealed by Heisenberg and his contemporaries, wasn't a giant machine operating with predictable certainty, but a realm of inherent fuzziness, where chance and probability reigned supreme. This new reality wasn't about chaos or a lack of order. Instead, it was a different kind of order, one where the fundamental building blocks of reality, the particles that make up everything we see and touch, existed not as miniature billiard balls with fixed trajectories, but as waves of probability, their properties intertwined in a delicate dance of uncertainty. This shift from a deterministic to a probabilistic worldview had profound philosophical implications. It challenged the very notion of objective reality, suggesting that the act of observation, the very way we interact with the universe, played a role in shaping the outcomes we observed. It was no longer enough to ask, where is that particle? Instead, the question became, what is the probability of finding that particle in a particular place at a particular time? This shift wasn't a descent into subjectivity, but an acknowledgement of the deeply interconnected nature of the observer and the observed, a recognition that we are not detached observers of the universe, but active participants in its unfolding story. This new understanding of reality, though initially unsettling, opened up new avenues for exploration, not just in physics, but in fields as diverse as philosophy, cosmology, and even art. It challenged us to rethink our place in the universe, not as passive recipients of a predetermined fate, but as active agents, shaping the tapestry of reality with every observation, every measurement, every interaction. Heisenberg's uncertainty principle, though a monumental achievement, wasn't the final word in quantum mechanics. It was a crucial movement in an ongoing symphony, a melody that continues to evolve and surprise us with its intricate harmonies and unexpected dissonances. Despite its successes, quantum mechanics remains a theory full of open questions and unresolved mysteries. The interpretation of the wave function, the nature of quantum measurement, the relationship between the quantum world and the macroscopic world we experience, these are just a few of the puzzles that continue to intrigue and challenge physicists today. New interpretations of quantum mechanics, such as the many worlds interpretation, have emerged, offering alternative perspectives on the nature of reality and the role of the observer. These interpretations, though often mind-boggling in their implications, demonstrate the richness and depth of the quantum world, a world that continues to defy our classical intuitions and challenge our very notion of what it means to exist. The story of Heisenberg's uncertainty principle is a testament to the power of human curiosity, our relentless drive to understand the universe and our place within it. It's a story that began with a challenge to the established order, a willingness to question the very foundations of our understanding. It's a story that continues to unfold, each new discovery adding a note to the grand symphony of quantum mechanics, a symphony that resonates with the profound beauty and mystery of the universe we inhabit.
If you enjoy this channel, don't forget to hit that follow button. Your support drives my creativity, and together, we explore the wonders of science. Let's make discoveries together. If you enjoy this channel, don't forget to hit that follow button. Your support drives my creativity, and together, we explore the wonders of science. Let's make discoveries together.